Okay, so welcome to MathStat 341. What I want to do for the next couple of lectures is talk a little bit about applications of probability to problems in the real world. And so this will be a good way to motivate a lot of the theoretical material that we're going to be looking at over the next few weeks. And so there will be some things that we will see just very, very briefly right now, and then we will revisit in much greater depth. And I'm hoping that by taking some time and looking at the material now, this will give you a motivation for why we care so much about all the different things we're looking at. The big lie from Calc 2 is that you can integrate. You can't, I can't, nobody can. We have to work really hard to give you functions that have nice closed form expressions. It's very similar in probability. There's a couple of distributions that we can work with in nice closed form that have all the different parameters and stuff that we want. And so fortunately, there's a lot of different choices for which ones we can look at, and they're pretty flexible. They cover lots of different items. And we can just hope that one of them will do a good job modeling what we care about. And so I'm going to talk a little bit about how you might try to sniff out which model to use over the next few lectures. There are a couple of other additional lectures that you can look at that are online from previous years. This is one of the nice things about recording the classes is I don't have to do the same advanced topic each year. So you can take a look at the other ones and see if it's something that interests you, watch it at 1.5 or something like that speed, get a good workout while you're doing it, okay? You probably noticed that this is a 2019 talk. The slides really haven't changed that much, so rather than just changing it so that it says date today, I'm just using an older version. This did lead to a paper that was published in a good journal with a couple of Williams students. So there's going to be a lot of opportunities during the semester as well as over the summer if you want to do some research to work. Friday, we have hopefully perspectives visiting us, and the class will be on the goat of goats, and it will be talking about some research problems in baseball that I'm working on with a colleague that I think people here would be very well prepared to work on. All right. I'm assuming people have a brief familiarity with World War II. So this is two different snapshots of what Europe looked like at the start of the hostilities and then in 1942. And you can see the remarkable advance that Germany made in terms of conquering nations. And a lot of this was due to a masterful use of tanks and attacks from that. Anybody ever see the movie Patton? Has one of my favorite movie lines of all time. So one of the great German generals, Rommel, wrote a book after World War II on tank tactics. So as a rule of thumb, be very careful what strategies of yours you share with the world. The great line in the movie after Patton beats Rommel in battle, "Rommel, you magnificent bastard, I read your book." And so it does help if you know what the enemy is going to do. Usually you don't have that fortune, okay? And you need to figure out how can you get the information you need. They're not always going to write a book on, here's my strategy. Well, before we can even figure out what to do, we need to know what kind of forces are we facing. So how many tanks do the Germans have? How many are they making? How many are they deploying to different parts of the world? Well, one possibility, of course, is to call them up and ask, excuse me, I'm a reporter for the London Times. I was wondering if you could give me your month. No, okay, that's not going to work. How could you find out how many tanks the Germans are producing? What could you do?
Figure out where they get the parts from.
So one thing is to look at where they're getting the parts and maybe look at how the parts are moving, especially if there's a few things that are extremely key. Maybe you need certain minerals or certain metals that are in short supply. How else could you try to figure out? Yes. So you could look maybe at the size of the factory, maybe try to get an agent into the factory. So there are direct measures we can do like that. Whoa, okay, it just takes a while to advance. Interesting, okay. Another possibility is to use math and stats. Which do you think does a better job, given that this is a lecture in a math stats class? The mathematicians, statisticians, or the spies on the field? I'm sorry? Yeah, math stats. This is one of the greatest successes, I think, of mathematics and statistics. Although you have to be careful. It's not enough to have the right answer. What do you also have to be able to do if you have the right answer? Okay, it's related to show that it's right.
One has to inform the strategy somehow.
Okay. make the people who need to listen, listen. So we're going to mostly talk about Europe today, but you can also look at the Pacific War. Initially, it was not going well for America. After Pearl Harbor, the United States suffered essentially defeat after defeat in the Pacific to the Imperial Japanese Navy. The Japanese had more aircraft carriers and they won a tremendous number of engagements. But we had cracked the main Japanese code, or most of it. And we knew that they were going to attack something designated AF-15. And if we know where they're going to attack and roughly how they're going to attack, we can commit all of our forces and catch them by surprise. Now, the problem with this is we believed AF-15 was Midway, but it could have been the West Coast. It could have been Pearl Harbor again. It could have been Australia. So when they told this to Admiral Nimitz, he goes, "You're pretty sure? I can't commit the entire fleet if you're pretty sure. Come back when you're sure." And the way the Allies found out that it was Midway is one of the most brilliant ideas I've ever heard in my life. And the reason I love telling the story, and I even have it as a picture on a cryptography book I wrote, is you don't need the most advanced mathematics to make the biggest contributions. If you can get nothing else from today, just get that lesson. So Commodore Rochefort, on a very secure channel, communicated with Midway. And he told them, "We want you to break one of your water pumps. And then in an unguarded transmission that's low priority or in a frequency we know the Japanese have cracked, we want you to just, in the middle of a routine message, mention that you have a broken water pump and will be out of fresh water in 2 weeks if you don't get a replacement." A day or two later, the Americans intercepted a message from the Japanese. The Japanese message said, "We've just intercepted an American message. AF-15 has a broken water pump and will be out of fresh water in 2 weeks." And at that point, Nimitz then went all in. So far all in that they actually took one of the aircraft carriers, which needed months of repair in Pearl Harbor, and they fixed it up enough to get it underway. And they just left the engineers and repair crews on it, fixing it as much as possible as it steamed to battle. They threw everything they could into the battle. It was the turning point of the war in the Pacific. And after that, I believe the superiority of carriers shifted from the Japanese side to the American. They lost 4 to 1 of our aircraft carriers. And this just shows you the power of just sometimes out of the box thinking, but also the need to be able to convince the people who make the decision to listen to you. All right, so here is how the problem is going to work. After battle, we are going to observe some tanks on the field with serial numbers S1, S2, all the way up to SK. So we will always observe K serial numbers. And we want to try to estimate either how many tanks were produced or how many tanks win the battle. We will assume that the first tank produced is tank number 1, then 2, then 3, then 4. Later, I will talk about how you generalize this to the tanks start with an arbitrary number and then are produced sequentially. Can anybody give an advantage of having the tank numbers sequential? Why might you do that? Yes. Yeah, so basically you'll have some idea of which tanks are produced together. So if there was a manufacturing issue, we know which ones to recall, which ones to look at. You know roughly how old the tank is quickly by looking at things. There's a lot of advantages. And it just wasn't suspected that you're giving away information. How many of you have ever been at a restaurant or bar or club that has a tip jar at the start of the night? And what do you notice in the tip jar at the start of the night? Okay, low, but not empty. Right. You start with money in the tip jar so people feel bad if they don't put it in, or if they see that there's money in the tip jar, they go, "Oh, this is a place where people tip." So a lot of times you want to hide exactly how much is coming in. So you might actually put a little bit in the beginning to just hide the fact that you've had nothing so far. If you're trying to decide whether or not you want to hire a company and they say, we're very excited, you're going to be our first client, you might feel a little concerned. And so when you look at the order numbers and whatnot, the order numbers are often encoded, but you don't want to be order number 1. That may not inspire such confidence. So there are tricks you can do where, if you completely randomize the numbers, you won't be able to do this kind of inference. And they do that now in many situations to try to hide just how much is being done. You want to give away as little information as possible. Or what could you do? Now, I'm sure none of our athletes who are exercising in the gym, when they see somebody come in and start going 216, 217, you can deliberately start with a different number to try to make people feel that you have more than you actually do. So there's lots of different opportunities. All right, so again, the original formulation, the tanks are numbered from 1 to capital N. We observe K tanks, the largest we see is little m. And then the new version, which I probably won't talk about too much in class, is just what happens if you start off at N1. Can anybody give me a lower bound for your estimate of N? N has to be at least how much? It has to be at least M. It also has to be at least K, but M is a better lower bound than K. So whatever math we're doing, we know it should be at least as large as M. Okay, now there are dangers of underestimating and overestimating. What's the first thing you do when you enter an elevator? You're extremely paranoid and you're with a lot of people. Yeah, you look at the capacity. Do you think that they have perfectly calibrated it? So if it says 2,000 pounds at 2001, it breaks and everybody plummets to their death? I hope not, right? Okay, so exercise, find it out. I'm not gonna assign that as homework. So do you think there's more of a danger in overestimating or underestimating the capacity? Yeah, there's more of a danger in overestimating the capacity and having too many people in the elevator versus not having as many people using the elevator as possible. Same thing for bridges. There are certain types of errors that are better than others. So when you're doing your analysis, you always want to protect yourself. Which kind of error is going to hurt me more? For a lot of sports teams, a lot of decisions on plays are like this. My wife used to teach at Boston College, and they had a quarterback who you just could not sack. You could not sack this guy. The reason is when you were about to sack him, he would just toss the ball up, and it would frequently be an interception. And he would take a bad play and make it worse. And there are times when you want to be very careful about what are your decisions, how much do you want to risk, what are the consequences. Can somebody give me a danger of either underestimating or overestimating the number of enemy tanks that you're facing? Either way. Good, so if you overestimate, you might put in too many resources to the battle and not have enough in other places. And if you underestimate, you wouldn't have enough and you could get your ass whipped, right? So there's dangers in both. One of my favorite lines or quips from Lincoln is during the Civil War, General McClellan was quite famous for building up good armies, but not actually using them in the field. And he always felt that Lee had more soldiers and he always needed more reinforcements. And Lincoln quipped, if General McClellan isn't going to use his army, I'd like to borrow it for a time. And there's the analysis, the paralysis by analysis, that you're always afraid, and if you don't have good estimates, you lose opportunities. Okay, so for the outline for the talk, and it's either going to be a 1 or 2 day talk, depending on how interested people are. We might do the second part next week. We might do it later in the semester. So I want to talk a little bit about mathematical preliminaries. Some of these we've already seen. Then I want to really concentrate on the original formulation of the German tank problem. And then I want to get into some things on the more statistical side. I want to get into regression, trying to find best fit lines, which we'll do a lot more of later in the semester, and conjecturing. So if somebody tells you what formula to prove, you have a huge advantage. What if you're not given the formula? Can you sniff it up? We talked about that earlier this semester when we looked at the product rule, I believe. And in the video, it talked about the probability for, I think it was A union B in terms of the various constituents. So how can we try to guess what the answer might be? What kind of data can we gather? What kind of simulations can we run to give us a sense? All right, so mathematical preliminaries. So most of these we should know, but just for completeness, n factorial is the number of ways to order n objects when order matters. 0 factorial is the Seinfeld rule. It is 1. There is one way to do nothing. N choose k is the number of ways to choose k objects from n when order does not matter. So think choosing people to be representatives rather than being officers. And then the binomial theorem is x plus y to the n is the sum of n choose k, x to the k, y to the n minus k. So these are very standard objects that we will be using throughout the semester. And again, all of these notes are going to be posted online. Okay, So we hopefully have seen Pascal's triangle a few times. The ones on the two outsides, and then every number is the sum of the numbers above to the left plus above to the right. And we talked about how you can prove this by story. So this is the famous Pascal's triangle. And the proof we did was this time based on who invited me to give the talk. I did Red Sox and Yankees. And so if there are n+1 people and we want a group of K, we either are fortunate and we don't have the Yankee fan and have to choose K Red Sox fans, or we do have the Yankee and then we have to choose K-1 Sox fans. And if you notice, the tops are always adding up to n+1 and the bottoms are always adding up to K. So this is proof by story, an extremely powerful technique, but sometimes hard to do. All right, now there's other relations in Pascal's triangle. If you notice, if I go along the second diagonal, 1 + 2 + 3 + 4 + 5 is what? Which is the number below 15 to the right? 1 + 4 + 10 is, which is the number one below. So every sum is 15. No. All right. 1 + 3 + 6 is 10, which is the number below to the right. So it seems like if I sum diagonally to the left, I get a Fibonacci, I get a binomial coefficient that's one row further down to the right. All right. We talked about looking at things mod 2 and just the beautiful structure that's hidden. And so what I want to do now is I want to prove that relation I mentioned a moment ago, that if you sum diagonally to the left, you get another element. Has anybody ever seen this relation before? I had not seen it for quite a while. It's responsible for the miracle that happens that gives us a closed form solution at the end of the day. It's often very hard in mathematics. Who are my econ people here? Okay, so you know how hard it is to get a nice closed form expression where I give you the values of the different parameters in the economy and you know precisely what's going to happen. You frequently have to resort to simulation because the problem is just so complicated and I can't tell you what's going to happen if I tweak this by a little bit. And in fact, in a lot of models, the mathematical models are so sensitive to the initial parameters that if you tweak them ever so slightly, it's almost chaotic and you get wildly different answers. So whenever you can get a closed form solution, a miracle has happened. This is responsible for the miracle that will give us a nice explicit expression to estimate the number of tanks based on the largest serial number observed and the number of tanks observed. So this is the miracle. So I'm going to prove it by induction. So the way induction works is you first prove the initial step, and then you show that if it holds up to a certain level, it holds for the next level. So we're going to induct on capital N for a fixed value of K. So the base case when n equals K is trivial because when n equals K, we have a sum from K to K of K choose K, which is just 1, which is going to be K + 1 choose K + 1. So if you just substitute everything when n equals K, there's nothing to do. So the way induction works now, it's like a ladder. We showed the first step is true. Now we show if it's true when we have n, if it's true when n is 1 more, then we can just walk up because we go from n to n + 1, n + 1 to n + 2, then n + 4, actually, sorry, we go from K to K + 1, K + 1 to K + 2, and walk up like that. So here's how the proof goes. So usually these proofs revolve around taking your expression at the next level and somehow sniffing out the previous level. Well, if I'm summing from K to n + 1, the inductive hypothesis is talking about a sum from K to big N. Okay, well, I'll just take the first part to be the sum from m equals K to n, and then I add n + 1, choose n + 1. Well, by induction, I get to assume my result is true for big N, and I'm trying to show it's true for big N + 1. So by induction, this sum is just n + 1 choose K + 1. I now add n + 1 choose K. Oh, that's the Pascal relation. And then it follows. So we now have our miracle. All right, we now have all of our mathematical preliminaries. All right, so now it is time to turn to the original German tank problem. And what I want you to do is I want you to conjecture. And if it makes you feel better, the fate of the free world rests on the decisions you're about to make. Some people get really pumped up when it matters. Okay? Can you give me any information? We know that the best guess for the number of tanks has to be at least m. We know at least that much. So my question is, how do you think it depends on m and k? So imagine I tell you that the best fit, the largest M I observe is 100. And you want to guess how many tanks there should be. Would you have a higher guess if I increased K or a lower guess? If I told you the largest value of M came when K equals 10, how do you think that would compare with the largest value of M being 100, but now K equals 50? That N would be low. So we think that as you increase K, your guess for N decreases because you expect to get, more likely to get a larger value of M. So if you have the same value of M, but for larger K, then probably N is smaller. Okay, so we think that the excess over M should be decreasing as we increase K. What if we increase M, for the same value of K? Do you think our guess should increase or decrease? It should increase. So can somebody give me a function that increases with M increasing and decreases with K increasing? M over K. So the simplest thing we can guess is it's M, it takes a while to move up. It's M plus some extra boost. The simplest guess for the boost is some multiple of M over K. I'm going to give myself the freedom to have a multiple. So B is just some constant. The simplest choice of the constant would be 1, but that's the simplest functional form that satisfies. Okay. It turns out this is remarkably close to the correct answer. And the constant is 1. And the only difference is we have this extra little -1 bookkeeping that we have to subtract. So the guess we made is quite close. And being off by 1 tank is not terrible. Now, one of the things that I really like to hammer home is whether or not any of our guesses are reasonable. So the question is, can you give me any values of K or M where I might have some idea of what the best guess for N should be? There are 2 values of K where we actually should have some intuition.
K equals M.
Good. K equals what?
M.
K equals M or N?
M.
M. Okay, so if K equals M, then that means we observe, say, 10 tanks and the largest one is 10. What would you then guess N would be? I mean, again, the larger K is, the more unlikely it is that you wouldn't observe anything larger than it. So that's possible. I think there's better guesses, but it's not a horrible start to guess or to look at the case when K equals M. What else could you look at? K equals N. When K equals N, then what will M be? K, which is also N. So if K equals N, then you've observed every tank. And your best guess for N damn well better be N. Well, if you look at what happens if K equals N, M equals N, and you get N times 1 plus 1 over N, so you get N plus 1 minus, you get N. Good. It gives the right answer in the extreme case when you observe every tank. What's the other extreme? Rather than K equals N, what's the opposite extreme? Okay, no tanks. Now, if we observe no tanks, we can't make any guess. So we can't go that extreme. 1. So imagine you observe 1 tank, and I tell you its value is 50. What might you guess the total number of tanks is if you saw 50? You have to get a number between 1 and N. What do you think the most likely number to get between 1 and N is? Yes, something like N plus 1 over 2, N over 2, something like that. That if I only have 1 observation from 1 to N, my best guess is I'm somewhere in the middle. And so if I only have 1 value, I would expect my best guess should be twice that. And there you go. And so it fits. So again, this is not a proof, but it gives us some confidence that this could be a reasonable formula. So these are called sanity checks. Whenever you can, always do sanity checks and see, can you trust the outcome? Okay. So here is the first real result that we're going to need to prove. So let M be the random variable. So we haven't talked too much about random variables, so this is a great way to introduce them. Class, random variables class. So we usually use capital letters for random variables. We usually use lowercase values for the value that they take on. So capital M is the random variable that is the largest serial number observed, and lowercase m is that value. And what this is telling us is the probability that we observe little m is equal to m choose k minus m minus 1 choose k over n choose k, or m minus 1 choose k minus 1 divided by n choose k. Bless you. And I'm saying this is only for m between k and n. Why would it be 0 if m isn't between k and n?
Well, you can't say anything greater than 10.
We can't observe anything greater than n.
And then for K, it's like observe the first K thing is the largest one. At the worst case scenario, you didn't want.
Good. Good. We can't have m, if we observe 15 tanks and they start with 1, 2, 3, the largest one we observe can't be 3. It's got to be at least 15. So clearly the probability is 0 if m is less than k, it's 0 if m is greater than n. We only have to figure out what's going on in between. So there's a lot of ways to look at this, and this is similar to some of the card problems we're looking at. What does the n choose k in the denominator remind you of?
Total number of possible hands.
Yeah, total number of hands. We're basically playing poker with the world's freedom, right? Instead of 52 choose 5, it's your n choose k. There are n serial numbers, we choose k of them. I want to know how many of those hands have the largest tank serial number being m. Well, m choose k is the number of ways to choose k tanks from m. That doesn't mean the largest serial number is m. It doesn't mean we chose m. It means the largest one we chose is at most m. We then subtract m minus 1 choose k. That's the number of ways to choose k tanks from m minus 1, where the largest serial number chosen is at most m minus 1. So if we look at their difference, the difference between them has to be all of the combinations that have a largest tank of m. We could get to this now immediately by using who's identity. This is just Pascal. This is just Pascal. M choose, just move this over to the other side. It's just Pascal. So if we use Pascal, we get this. Or we could prove Pascal's identity right now by counting tanks. The other way is, imagine our largest tank is m. So we have to choose that tank. That's a 1 choose 1, which I'm not bothering to write. And now we have m minus 1 serial numbers that are less than m. We have to choose k minus 1 of them. So this is going to be the number of ways to choose k tanks where the largest serial number is m. Okay. And I've just written out the text over here, just a little bit explicitly. Okay. So now we haven't done the expected value formally, but to some extent, I think everybody here knows expected value if you've taken any class that grades. Final is 40%, midterm is 30%, homework is 20%, class participation is 10%. And if you want to figure out what your grade is, you multiply your final by 0.4, your midterm by 0.3, your homework by 0.2, and then your class participation by 0.1. And that will give you, this nice weighted average. And later in the semester, we'll talk about other types of averaging. So the expected value is the standard average value. For each value, I weight it by the probability it happens. This is one of the most useful concepts we'll have all semester. It's really nice if every event has the same probability. Can you give me something where all the events have the same probability? A deck of cards. Each card has probability 1/52 of being chosen. What else? Coin flip. Now, if you practice, you can actually learn to flip consistently heads or tails. And that could be a very valuable skill to develop. Rolling the fair die, the numbers 1 through 6. We are not in a situation where everything is equally likely. So if we put in the probability from the previous slide, it's m minus 1 choose k minus 1 divided by n choose k. And that's the expected value of m. So we want to calculate what this is. Does anybody have any thoughts about how we might do this calculation? We have to execute this sum. And it's a sum over m. So what might we do? So what do you know about binomial coefficients? What is 7 choose 3? It's 7 factorial over 3 factorial, 4 factorial. The first thing that we might want to do for something like this is, well, maybe we should expand out the m-1, choose k-1. We have an m over here. You can see the m is basically begging to be included in here, and then get a whole binomial sum that you could do. This part over here has no m dependence. We can even pull that out. So again, you want to learn how to look at equations. And this is why I really want to spend class time emphasizing not just doing the algebra, but how you should think about doing the algebra. When I see something like this, I see the m all by itself. It wants to be included. It wants to come on over. So let's help it. All right, so this is the algebra. And the more lines you have, the more painful it can sometimes be, but it's pretty straightforward. I expand out what everything is. And because the n choose k is in the denominator, I flip it up. All right, so the m hits the m-1 factorial and becomes an m factorial. I have a k-1 factorial. It really wants to be a k factorial. So to make this a k factorial, I multiply by k over k. And that's why I have this k up over here. Now I have m factorial k. The 2k factorials over there. I could cancel them, but I've got an m factorial over k factorial, m minus k factorial. That looks like an m choose k. So rather than canceling the k factorial, it's better to keep that as an m choose k and then pull out everything that doesn't depend on m. And now we have a sum, m goes from k to n of m choose k. In a wonderful act of foreshadowing, right, earlier in the lecture, we talked about identities for sums of binomial coefficients. And here's the miracle. We actually have a closed form expression for this. It's now just n plus 1 choose k plus 1. So what should we do now? How could we simplify this further? Yeah, expand the n plus 1 choose k plus 1. So if we expand the n plus 1 choose k plus 1, we then get n plus 1 factorial over k plus 1 factorial n minus k factorial. Oh, okay, I've got a k factorial, a k plus 1 factorial. That's going to become a k plus 1. So I'll have like a k over k plus 1. I have an n plus 1 factorial over n factorial. That's going to become an n plus 1. The n minus k factorials cancel. No, I mean, it is absolutely beautiful how much it cancels. And you get n plus 1 multiplied by k over k plus 1. Oh yeah, so much of mathematics is about looking at things the right way. This is why, have I brought in the Rubik's Cubes to this class yet? Where if you look at the Rubik's Cube the right way, it's trivial, it's a 3 by 3. If you look at it the wrong way, it's painful. And I remember I had one of those, cubes. It was all one color and it was also the angle. So they did both to you. They got rid of the color and they got rid of the standard. And I was trying to solve it at one of my daughter's baseball games. It was one of the few years I wasn't coaching. And I was just stuck. And then the next morning, when I was kind of tired, I was, oh, if I just turn it like this. And it's that aha moment. And the goal is to try to help you get aha moments as much as possible. The more of these things you do, the easier it's going to be to get one of these aha moments. Well, we can now simplify. So if we know that the expected value of m is k over k plus 1 times n plus 1, I can then solve for n. And so n is going to be the expected value of m times 1 plus 1 over k minus 1. And there's our formula. So now our best guess for n is to put in the value we observe for m. And there's our proof. So we now have a theoretical formula. And we can try to see how well it works. Okay, any questions on what we've done so far? So we've done a tremendous amount. We've reviewed some basics of probability. We've introduced some new concepts in random variables, expected values. We've also talked about how to conjecture formulas and how to test if your conjectures are reasonable. One of my students did one of these sanity checks when he was working in an investment house, and he just got, this doesn't make sense. And it turns out a minus sign was dropped. And it was really good that he had done some of these checks before they executed certain things. So whenever you can do simple checks, strongly urge you to do so. Okay, so the next question is to try to generalize this. Out of curiosity, how many people here have taken a stats class at Williams? Okay, so a good number of you. It is not a prerequisite for this class, but I want to try to make sure that I do occasionally throw in some stuff for the people who have seen stats as well. If you haven't taken a real basic stats course, I strongly urge you to consider doing that as well. So what if we try to tweak the problem? So now we start off at N1. So this is like the person who's doing, weights, and they start saying, 200, 201, somebody walks into the room to make it sound like they've done a lot more. So we start off with a higher number, but we're still going to number things consecutively. And so we'll talk now about the spread, the difference between the smallest and the largest observed serial numbers. And we want to try to estimate how many tanks there are based on the spread and based on how many tanks we observe. Now, one of the things you have to be careful about, which is a little bit annoying, is let's say I go from 3 to 5. Okay, what's my spread? 2, but how many numbers are between them? 3. So you have to be careful that there's often a little +1 that's going. So the number of tanks is the difference between N1 and N2 +1. So you just have to be a little bit careful about that. In the special case, when N1 equals 1, you get -1 + 1, and it just nicely cancels out. So what I want to do is I want to try to estimate what N should be in terms of the spread. Can anybody, and the number of tanks observed K, can anybody give me a lower bound for N in terms of the spread S and the number of tanks observed K? It has to be at least well, I want to know how many tanks there are, and I tell you the spread is S, and I observed K tanks. Can you give me a lower bound? And if you're off by 1, I don't care. It has to be at least S, right? If I observe a spread of 8, there have to be at least 8 tanks made. And now let's ask the same question as before. If I increase S for fixed K, do you think there are more tanks or fewer tanks? If I tell you the spread is 100 with 2 tanks, would you guess that there were more tanks than if I told you there were 100 tanks when K is just 2? I'm sorry, let me say it again, sorry. We have 2 tanks. In one case, I tell you I observe a spread of 100 with 2 tanks. In the other, I tell you I observe a spread of 10 with 2 tanks. Do you think there were more tanks with the spread being 100 or the spread being 10? 100. That is, the spread increases for fixed K, I expect the estimate for N to increase. What if I have the same spread, but more tanks? Do you think my guess increases or decreases? Decreases. So what would you guess for the formula? So it should be S plus so I want something that increases with S and decreases with K. So one thing is to try to guess S over K. And of course, we could put in this free multiple B. So do I have the same guess as you? Almost. So what's the difference between my guess and your guess? I have a K minus 1. Anybody have any thoughts as to why I have a K minus 1? So there is the advantage of having worked on the problem for several years and knowing where it's going. It's very similar to the degrees of freedom. If I give you one observation and tell you your life depends on estimating the mean, I observed a 73. What would you guess for the mean? Your life is depending on this. That's the only information you know. You observed a 73. What's your best guess for the mean? 73. You observed a 92. What's your best guess for the mean? 92. Is it possible to guess or estimate the mean based on one observation? I'm sorry? Yeah. It may not be a good guess, right? It's not going to be as good of a guess as if you had 100 data points, but you can still guess the mean. Now imagine I want to talk about how spread out a distribution is. I want to talk about its variance or its standard deviation. And I only give you one measurement. So you have a normally distributed random variable. How many of you know what a normal random variable is? Right, so most of you have seen a normal random variable. You have a normal random variable and I observe the value 73. You would guess 73 for the mean. Do you have any information at all about what the variance should be for that normal? No, with one observation, you can't estimate how things vary. Things need to vary for you to be able to estimate how things vary. If you only have one observation, you can't do it. So I should not be trying to estimate, based on a spread with only one observation, because there is none. And this formula basically blows up. Now, what's nice is if k equals 1, what does s equal? If you only have one observation, what does s equal? 0. So you have 0 divided by 0, which is the classic get out of jail free in pure mathematics. It means I am saying nothing about what this is. It's undefined. So the formula knows that you should not be trying to make any guesses. This is a little bit similar to if you've done some sample variances. Are you dividing by the number of data points or one less than the number of data points? So if you've seen some statistics, these issues do arise. It's better to estimate with a k minus 1 than with a k. Now, if k is large, this is going to be a very small correction. Hopefully you don't just observe, 1 or 2 tanks. Hopefully you observe a good number. All right, and so we can then, do some theoretical work, and it turns out the answer is a 2. And before we had a 1, so the b actually is equal to 2 this time. Anybody want to give me any thoughts as to why there might be a 2? Is that surprising? Yes.
Well, that's just like, is that saying that like there's going to be like a bigger than observed spread?
Not a bigger than observed spread. It spreads on both sides, right? Before here, we knew we were only going in one direction. Here, we can be going in both directions. So you might naturally put that in, or you might do some kind of retroactive, oh, of course, it's natural that there's a 2 there, because we can be going, it's at least like a reasonable story to tell. And then we need to just figure out, what is the probability. So I'm not going to go through the details of this calculation, but you can write down an explicit formula for what the probability of a given spread is. It's a little bit more involved, okay? But it's calculated in a very similar way. And we go through all of this in detail in the paper that I wrote with the students. And then the rest of the proof is similar to before. It's just more details in terms of more algebra. I will just quickly go through those slides because I want them to just be part of the video so that you can always just hit pause if you want, but I will link to the slides as well in the talk. Frequently in the proofs, we have to multiply by 1 or add 0, sometimes in moderately clever ways, sometimes in pretty standard ways. When we had that k minus 1 factorial, we saw that it really wanted to be a k factorial, so multiplying by k over k was a somewhat natural thing to try. All right, and then what I want to do is just, yeah, it's good. How many of you use LaTeX? So if you're doing anything in Beamer for presentations, I really like the city Darmstadt as the theme, because it gives you the little circle dots and you can just click on a dot and move to any part of the talk very quickly. So I skipped over the regression session, I skipped over the implementation issues, I skipped over the references, and I just jumped here. And so we'll save the other stuff for either Monday's class or later in the semester. And so these are the details for what would happen if we don't know the lower bound. So we just have a little bit more notation. We have a N1 and N2, a big M1, a big M2. We have the probability. And now we want to calculate the expected value of the spread. And we just have a little bit more algebra to do. And a little bit more algebra to do after that. Okay, it's interesting. It moved on the screen here before it moved on the screen over there. So for a while, they were in different zones. All right, so we do a little bit more algebra when we get to this point. Then we continue to do some algebra. And after doing a little bit more algebra, we have an expression for T2. And we then split T2 into 2 different sums. You can begin to notice how much worse this is. And then after we do that, we then continue with the analysis to handle the different terms. We get T22, we get T21, we get the expressions for them. And then eventually, after we do even more algebra, the dust settles, and we finally get a value for the expected value of S, as n plus 1, k minus 1 over k plus 1. So very, very similar to what we had before, which is nice. And then once we have that, we can then solve for the best fit value of n, and we'll get S1 plus 2 over k minus 1. And that is it. All right, so any questions on what we've done today? All right, so I'm going to stop this.